So just to recap what we've done, in the analytical portion, you were asked to calculate the electric field at 1 millimeter away from the charge using the analytical equation. We repeated that same effort in Maxwell 3D using the computational approach, and we evaluated the point at x equals 1 millimeter. So same as the radius of 1 millimeter, but we just limited it to the x-axis, evaluated that point. We evaluated the point on the y-axis at 1 millimeter, and then we did the same at the z-axis at 1 millimeter. And if you compare the difference between those results, they're each a little bit different. For whatever reason, the point located on the y-axis gave us the smallest amount of error. If you just simply compare the value that we got to the analytical estimate, and the x and y point for some reason gave us a larger error. So this is a really good opportunity to discuss what's happening with the computational solution and try to explain where these differences might be coming from. I'm going to right click on the top level node that says Maxwell 3D Design 1, and I'm going to copy it, and I'm going to simply paste it on top of Project 1. And the whole point of this was to go make a change on the setup. And I'm going to look at the percent error and change it one order of magnitude. So instead of 0.1%, I'm going to bring it down to 0.01%. And I think for now, that's going to be the only change that I'm going to make. And I will just go ahead and validate and analyze all. So while that's solving, I'm going to double click on Design 1, and I'm going to plot the mesh. So let's choose the global XY plane. And if I right click, once that's selected, I can come down and find this plot mesh button. And I'll go ahead and let it stay on a last adaptive paths. And I'm going to turn off the geometry. So if I select the region, I can Control H will hide it, and the sphere, Control H will hide that. And now I'm going to highlight the mesh and get a normal view here. And as I zoom in, I can see the profile of where that geometry was that's now been hidden. And I'll come back to this in a second. I'm going to go back to Design 2 and do the same. My solution is now complete. Before we look at the results, I'm just going to go grab the plane, XY, and I'll right click and I'll plot the mesh on this. And we'll do the same. I'll go ahead and hide the region. This time I'll just hit the X. I'll do the same with the sphere. And I'll orient it with the Z. Double click this to keep the mesh on, and I'm going to zoom in and see how close I can. See if we can get a view of the same thing here. So about the same profile. Another thing I can do is I can hit Control 2, and I can get all these views in one screen. So let me just kill all these other windows, and I'm going to hit Control 2 one more time, and it'll give me kind of a side-by-side comparison of these two. One thing that should be pretty noticeable here is that this Design 2 seems to have more elements. And that's what this mesh is. Everything you're looking at here is a 2D cross-section of the tetrahedral elements. And so basically on a 2D view, they look like triangles. And I can see that this definitely has more around the area here. I can prove that by going into my solution. So if I go into results for Design 2 and look at the solution data, I can just go straight to mesh statistics, and I can look at the number of tetrahedra. This says total number of elements is 63,000. So almost 64,000 elements for Design 2. Now, if I do the same for Design 1, and I'll double click that, I'll go to Solution, and mesh statistics, I'll see that number is about half. So this is telling me that it ended up with more elements as I expected, and more than likely it's going to give us a result that is probably going to be a little bit closer to what the analytical result was. So let's look at that. I'm just going to expand out design 2, and I should have updated results now. So calculator expression 1, I'll just read that value off, 9.02 times 10 to the 15, and I'm going to plug that in to my modified spreadsheet here. So I'm comparing the error between design 2 and design 1. So the previous error for the point at x equals 1 millimeter was 1.56%. That error has come down to 0.33%. So quite a bit of improvement. And if I go back and do the same for the y-axis point, that's, let's just say 9.00, I'll plug that value in. So that turns out to be the same. It's the same distance away from the analytical, basically just in the other direction. So that was already a good result. That stayed the same. And my last one was to go off of my 2D plot and look at the marker location, which is now, looks like 9.02. So I'll plug that number in, 9.02 e to the 1/5. And that is also improved, just like the X position did. So in the updated solution with more mesh elements and higher convergence criteria for 0.01, all points either stay the same or improved. So this is a concept that we'll probably come back to multiple times as we go through various lessons and scenarios with different finite element solvers. It's very common to see behavior like this, where we'll see large mesh elements where maybe the fields are not changing very rapidly, and then we'd get very dense mesh cells where that vector field is actually changing quite a bit with position. So hopefully you got a good feel for this. This is a pretty good illustration of how that works, and we'll certainly be coming back to that over time. And that's the end of this segment.